Welcome everyone, this is the second sub-module of 3 on horizontal drilling, extended reach, geosteering and multilateral well course from Next Training part of SLB. By the end of this module you will be able to list the major directional drilling methods and the major directional drilling enabling technologies. In the world of directional drilling we need to use equations to define where our well path is. An example of this is the equation of the relationship between radius of curvature and the build-up rate commonly seen in directional drilling math. In later modules we will go much deeper into these equations and solve some fun problems. Let's start with definitions and refer to the diagram at the bottom right of the slide. RC, or radius of curvature, is defined by the radius of the arc that the wellbore follows during deviation. In simpler terms, it is the size of the circle that the curved section of the well would complete if continued indefinitely. The tighter the curve, the smaller the radius of curvature. Build-up rate refers to the rate of angular change of the wellbore trajectory per 100 feet of measured depth, typically expressed in degrees per 100 feet. It indicates how sharply the well path is changing direction. These two parameters are inversely related. A higher BUR corresponds to a smaller radius of curvature. This relationship is crucial because it directly impacts tool selection, wellbore stability, completion design, and operational planning. Directional well profiles are commonly categorized into 3 types based on their radius of curvature and build-up rate: short radius, medium radius, and long radius wells. Let's go through each of them. 1. Short radius wells. These are characterized by very high build rates, which are typically greater than 35 degrees per 100 feet, with a radius of curvature of less than 160 feet. These wells are used in highly specific or niche applications. For instance, they may be deployed in mature fields where re-entry into an existing wellbore is required to target bypassed zones or sidetrack into a new zone close to the original wellbore. Due to the extremely tight curvature, specialized and highly flexible bottom hole assemblies are needed. This includes coiled tubing drilling tools, which are more maneuverable in tight radii. The operational complexity and tooling requirements make short radius wells relatively uncommon and more expensive, but sometimes necessary for maximizing reservoir recovery. 2. Medium radius wells. These are defined by build-up rates between 6 and 35 degrees per 100 feet and radius of curvature ranging from 160 to 1000 feet. This is becoming a more commonly used range in modern directional drilling, thanks to technological advancements, especially in rotary steerable systems, RSS, and positive displacement motors. Above 6-degree dogleg, it is important to start measuring fatigue life on tool components in order to reduce the risk of drill string failure. 3. Long radius wells. These are characterized by build-up rates between 2 and 6 degrees per 100 feet and radius of curvature between 1000 and 3000 feet. These profiles are normally the most common. The benefit is reduced torque and drag because lower doglegs result in a lower normal force of the BHA pushing against the side of the hole. A lower BUR reduces mechanical stresses on the drill string and casing. Long radius wells are often used in extended reach drilling ERD, especially offshore, where the reservoir target lies several thousand feet horizontally from the surface location. Since the curvature is mild, all types of steerable BHA, including conventional motors and RSS, can be used. One key advantage is that the smoother well path supports better casing installation and efficiency. Before I move on, here is a question. What type of well profile does not cause a concern about drill collar fatigue life caused by rotating bending stress? Is it short, medium, or long radius? I will pause momentarily for you to think on this. The answer is long radius. But the caveat is that this is related to rotary steerable BHA, as this is when the drill collars are subjected to bending stress as they rotate through the dogleg. This does not occur during sliding, which is how a motor builds angle. Let's now step back in time and explore how directional drilling started. Before the advent of modern tools like directional mud motors and rotary steerable systems, early directional drilling relied on far more rudimentary methods. This slide provides an overview of the three main historical techniques used to intentionally deviate a wellbore. These were the retrievable whipstock straight motor with a bent sub and jetting assemblies. 1. Retrievable whipstock. These were the earliest methods for initiating a sidetrack or deviating a wellbore. A whipstock is a mechanical wedge placed in the wellbore to guide the bit in a new direction. Think of it like a ramp that deflects the bit off the vertical path. The whipstock was typically anchored in place and would cause the bit to deviate as it followed the sloped face. However, the technology had significant limitations. While whipstocks introduced the basic concept of changing wellbore trajectory, they were unreliable, lacked precision, and were restricted to specific formation types. Today, modern whipstocks are significantly more advanced and are still a possible selection for deviation. 2. Straight motor and bent sub. These became available in the mid-1960s. This system included a mud motor, which uses drilling fluid flow to turn the bit independently of the drill string, a bent sub, which creates a slight angular offset, typically less than 2 degrees between the drill string and the motor. The motor and bent sub were oriented in the desired direction of deviation. The bit was advanced while sliding, meaning no rotation of the drill string from surface, only the motor turned the bit. This allowed the wellbore to bend gradually in the direction of the bent sub. However, the drilling was limited to sliding only, which increased drag, made weight transfer difficult, and reduced the rate of penetration, or ROP. They were used with roller cone bits at low RPM, which had limited bearing life. The tools also had limited steering capability, and a lot of flat time was incurred off bottom reorientating the motor. 3. Jetting assemblies. The third method refers to the use of high-pressure mud jets through specially designed bit nozzles to erode the formation and steer the bit. Instead of mechanically pushing the bit to one side, as with a whipstock or bent sub, jetting relies on hydraulic energy to wear away the rock in a targeted direction. Jetting sometimes finds application in shallow kick-off procedures, or when initiating soft formation deviations where tool costs need to be minimized. It also has a place when steering where there is tight anti-collision, because the only force enabling the BHA to progress is the jetting force, which is low risk. However, it has largely been replaced by more reliable and accurate technologies. Okay, so question, which method would I use today for a top hole deviation in soft formation? Would it be a whipstock, motor with a bent sub, or a jetting assembly? I will give you a moment to think. Well, in a top hole soft formation, it can be hard to get deviation with rotary steerable and motors because the formation is so soft that it is being washed away ahead of the bit, preventing efficient operation. So, in a situation like this, using a jetting sub would be a good choice. Okay, let's move on. Directional drilling has dramatically enhanced our ability to drill with precision, efficiency, and safety. As seen in the timeline at the top right of the slide, directional drilling technology has been evolving since the 1960s. We began with positive displacement motors, PDM, and bent subs, rudimentary tools that allowed some deviation from vertical drilling. This was a significant breakthrough at the time, but came with limitations in control and predictability. The 1970s brought in the wireline steering tools, followed by the advent of measurement while drilling MWD technology in the 1980s. This was transformative. It gave drillers real-time feedback on parameters like inclination, azimuth, and tool face orientation. Soon after, steerable motors were introduced, which improved control by allowing changes in trajectory without tripping the drill string. Finally, rotary steerable was introduced in the mid-90s. Initially unreliable, they quickly improved and delivered a step change in performance and its ability to access the flanks of reservoirs not possible with motors. These technologies yield significant benefits in longer runs and fewer trips, resulting in less downtime and lower operational expenses. These technologies are also an enabler for extended reach and multilateral wells. As we move forward, we can expect these technologies to become even more autonomous, intelligent, and integrated, driven by AI, machine learning, and advanced cloud analytics. Okay, question time. What technology came along that opened the opportunity to drill a section in one run? I will give you a moment to think. So, in order to drill a section, we need to know where we are going. Initially, this was done by running a single shot or even a wireline steering tool, but this could be done while the BHA remained in the hole. What really changed drilling was the use of steerable motors. This allowed directional changes to be made, then continued drilling without the need to pull out of the hole. The MWD tool would send up steering readings in real time, so the directional driller knew the direction they were heading and could orient the BHA to the required direction. Also, since the bend in the motor was small, the BHA could be rotated as well, enabling drilling ahead without continuous steering. Let's now shift focus to a critical component of directional drilling, which is wellbore surveys. If modern directional drilling is about reaching increasingly complex targets with greater precision, then wellbore surveys are the navigational tools that make that precision possible. Without accurate surveying, even the most advanced rotary steerable system is flying blind. Wellbore surveys describes the position of the well path and defined by depth, inclination, and azimuth. So, why are surveys required? Why go to all this trouble to constantly survey the wellbore? Well, the reasons are both practical and regulatory, and they're vital to the success and legality of any drilling operation. 1. Satisfy regulatory agencies. Most jurisdictions require that operators submit accurate wellbore location data to government or regulatory bodies. This is especially important in offshore environments where multiple wells may be drilled from a single platform. Survey data ensures that we stay compliant and avoid legal issues. 2. Stay within lease boundaries or limits. Oil and gas leases are carefully defined by boundaries. Drilling outside these limits, knowingly or not, can lead to legal disputes, fines, or even the loss of mineral rights. 3. Construct accurate subsurface maps. Surveys contribute to the building of subsurface geological and geophysical maps. These maps are used not only for navigation but also for reservoir modelling, reserve estimation, and field development. 4. Determine location and control the wellbore path. Surveying is essential for real-time trajectory control. When drilling, we don't just hope the well goes where planned, we measure and adjust continuously. 5. Reach a target by steering. Ultimately, directional drilling is about hitting a target that may be miles away horizontally or vertically. Surveys enable precise course correction to ensure the bit is always moving in the right direction. This is especially important in horizontal wells, multilateral wells, and extended reach drilling, where margins for error are extremely tight. Okay, question. What information do I need from the MWD to calculate the position of the BHA? I will pause for a moment to let you think about it. Well, in order to calculate the position of the BHA, I need the inclination and the azimuth from the MWD. The depth I get from the surface is usually measured from a sensor on the drawworks. In order to calculate its position, I will then need all the other surveys back to a tie-in point, which is a defined 3D position. This often is at the rig floor or mean sea level. We then use each survey to iterate from this point, adding the additional displacement and direction from each survey. Now we are going to be more specific about the directional technologies, starting with the MWD. This is a vital component of modern directional drilling, enabling real-time monitoring and precise measurement of the well trajectory. Without it, directional drilling as we know it today would be impossible. MWD stands for Measurement While Drilling. As the name suggests, it refers to the process of gathering measurements, particularly directional and environmental data, while the drilling operation is ongoing. The data is transmitted to surface in real time. There are 3 different systems which can be used. First, mud pulse telemetry. This is the most widely used form of telemetry, especially in deep or offshore wells. The tool momentarily restricts the flow of mud to create pressure pulses. This enables binary data in ones and zeros to be sent to surface. This is the most common type of communication used. Second is electromagnetic telemetry. An EM pulse is sent into the formation, and a receiver at surface decodes the data. The data rate can be quicker, and the system is relatively simple and cheap, used for high-volume land operations. Wired drill pipe is the least used. It communicates data through the drill pipe, enabling high-bandwidth data transfer. This is excellent in deep water applications where the day rates are very high and minutes matter. These tools send a continuous or near continuous reading of inclination, azimuth, and tool face orientation, or TFO. As a quick aside, a tool face orientation is used by a directional engineer to help steer a PDM. Okay, question. What is the most common form of telemetry used today for MWD tools? I will give you a moment. The answer is mud pulse telemetry. EM telemetry is common in shallow wells on land but has limitations. Wired drill pipe is common in deep water applications. Alright, as we reach the end of this module, let's take a moment to review what we've covered and reflect on the key learning objectives. In this submodule, which is 2 of 3, we covered some of the calculations used in drilling for surveying, including how to determine the radius of curvature and build-up rate. We established the rate of build-up into short, medium and long radius wells. We looked at the 3 different ways a deflection could be achieved in the past through the use of whipstocks, straight motors and bent sub and jetting. We then looked at the evolution of the technologies into recent history. Then we moved on to look at wellbore surveys and why we take surveys. Finally, we looked at the MWD tool, what it does and how it works. In the final submodule, we will look at motors, RSS and LWD. From there, we will touch on formation evaluation, and then we will move on to geosteering, which utilizes the LWD data in real time to steer the bit in the optimal geological zone. This concludes submodule 2 of 3 on applications, objectives, and limitations. Thank you for listening. This ends the submodule 2 of 3. I hope you have found it very informative. Please progress to the quiz.